performance vendors, application vendors, compiler vendors, framework vendors. So we have a good representation from the industry, which is important because Kronos has been driven by its members. We want to be creating the APIs that are solving real problems for real companies making real money in the market. So over the years, it's been interesting to see how the APIs that Kronos creates have been changing in character to meet the evolving needs of the industry. When we first started out about 12 years ago, we were primarily focused on APIs for high-end desktop. OpenGL, many of you might be familiar with the cross-platform 3D graphics standard. OpenCL for parallel computation. Over the last few years, though, of course, mobile has become the platform where lots of innovation is happening in the industry. So now we need mobile APIs that provide almost the same level of sophistication as you can get on the desktop, but do it at much lower power levels and much lower footprint for cost-effective deployment in the mobile space. Where we are right now, augmented reality is really the key driver in this. Yesterday, the APIs that we created could exist independently of each other. You could have a graphics API, you could have a video API, and they didn't really need to talk to each other that much. It didn't really matter. Now we're trying to enable applications like augmented reality, the graphics and the video, and all the other subsystems, the sensor fusion has to be seamless. And these APIs, they have to work together. And I'll try and show you in the next few minutes how we're working to make the Kronos APIs into a coherent API ecosystem. Then last but not least, HTML5. The web, and particularly with HTML5, is becoming the promise of a cross-OS, cross-platform development environment. So we don't just need native APIs anymore. We need to start enabling web developers to have access to the same level of sophisticated acceleration as native application developers. We're not quite there yet, but we are making the first steps, and I will show you how that's working out at the end of this presentation. So that's a quick snapshot of some of these APIs that you're going to hear the silicon vendors talk about in more detail. OpenGL, yes, probably many of you are familiar. It's probably the most widely deployed Kronos API for 3D graphics. ES stands for Embedded Systems. So it's the OpenGL that's now close to 20 years old and has all of the latest 3D functionality streamlined down for deployment in mobile and embedded devices. It's now shipping in hundreds of millions of devices. Pretty well any 3D capable device is running or capable of running OpenGL ES. OpenGL ES 2, its latest version, is fully programmable, and it's capable of supporting some of the highest-end gaming engines, like Unreal Engine 3 from Epic. You're beginning to find console-class games and content beginning to ship on these mobile devices. It's getting pretty hard to tell the difference between a current generation console and the latest generation mobile devices. We have OpenCL, so G for graphics, C for compute. OpenCL is a framework for heterogeneous parallel programming. It means, what does that mean? That means that you can write software that will run across any of your processing elements you have in the system. It might be multi-core CPUs, it might be a programmable, highly parallel GPU, you might have DSP chips in there. OpenCL provides you a framework where you can write your software once and then run it in parallel across any of the compute resources that you find in your system. So there's a couple of APIs to find out what's in your system. You have a parallel programming language, which is very close to ISO C99, where you write kernels for your computation, and then you have a runtime API that lets you compile and distribute your kernels across your parallel resources and bring back the results. We're never going to need an OpenCL ES because we learned our lesson from OpenGL. and the core OpenCL specification already has an embedded profile built in to OpenCL, the domain specification. So we're already beginning to see OpenCL beginning to ship on mobile devices, primarily first with the embedded profile on mobile. OpenMax AL is a API that provides a lot of functionality around the camera, low-level image processing, pipeline imaging close to the sensor, and video processing with AV sync, audio sync. It's an object-oriented API. It's easy to use. Some of you might have come across OpenMax IL, which is intended for multimedia framework integration. That was never really intended for portable applications. OpenMax AL is the application layer of the OpenMax family. And so if you're using developing applications that uses camera, imaging, and video processing, I strongly recommend you check out OpenMax AL. It's going to be easier and more portable. I think OpenMax AL is going to be key in enabling some key use cases like advanced imaging, like computational photography, HD video teleconferencing with full hardware acceleration, and of course, augmented reality. You have OpenSLES, S for sound or audio. So what OpenGLES does for graphics, OpenSLES does for audio. It's object-oriented, just like OpenMax AL. It gives you advanced audio, including full 3D positional audio, which can be key for many augmented reality applications. One of the key problems I mentioned earlier was getting the video and the graphics subsystems to work together. It's surprisingly hard to get the graphics and the video communities to cooperate together. It's been an outstanding problem for many years, but now we actually have a solution in place. We can have, for example, the video subsystem using OpenMax AL, the 3D GPU using OpenGLES, and now we have a new extension to the EGL API, which isn't as well known as OpenGLES. It's often the forgotten API, but it's becoming increasingly important because it's the API that acts as the hub that lets the other APIs communicate together. And EGL Stream is the latest generation of the EGL functionality, so we can have a stream of video frames passing from the video subsystem into the graphics subsystem through a high-level, easily understood API that lets the application developer control that stream but not get too bogged down into the details, and it gives us a level of abstraction so the hardware vendors can optimize that transfer from video to graphics with no copies for their particular architecture. Some of the newest APIs that we have are expanding the reach of the types of hardware that the Chronos APIs are handling. Stream Input is our second newest API now, and it's trying to address the issue that mobile devices are getting richer and richer sensor networks built into the device itself. We need the application developer community to be able to tap into the power of the sensor network, but to do it in a portable way, so you don't have to rewrite your application for every different type of sensor you find on different types of platforms. The way that Stream Input is attempting to do that is to define semantic level information. So an application can request from the system, can you tell me about skeleton tracking information if you're doing a Connect type game, or can you give me gesture information if you're wanting to do a gesture UI, or define virtual sensors such as tell me if I'm in an elevator, or tell me if I'm being driven in a car, give me a callback, or if I'm being carried in a hip pocket, or I'm being carried in a backpack. The sensor guys know how to use the sensors on a device to give that kind of magical awareness to a device, to let it respond in a much more powerful and natural way to the way that the user is using it. So Stream Input will take that request, will create a network of processing to provide that semantic information back to the application. We really don't want to be forcing the application developers to have to look at each sensor individually, you lose the opportunity for the middleware and hardware vendors to provide sensor fusion innovation. And Stream Input is beginning to address some long-standing issues that make it very difficult to create a high-quality augmented reality application. For example, how do you synchronize your camera input with your gyro input? The processing pipeline lengths are very different for both. So unless you have some synchronization mechanism, it's difficult to have your sensors being used correctly. And Stream Input is addressing that with universal timestamps for each of the sensor streams. Kind of sounds like a ambitious thing to do, and in some ways it is, but we have some really key participants in the industry that are helping us define Stream Input. So for example, some of you may know PrimeSense. They are the technology vendor for the depth